Hello, everyone. I'm excited to introduce to you today a great discussion and learning opportunity with our guest speaker from Harmonic. Today's presentation will provide a basic understanding of Remote PHY, why we're moving toward it, and a basic understanding of passive optical network and fiber systems. I'd like to take a little bit of time before we get to the presentation and walk you through our mission and some other information from SCTE. We strive to be the best chapter in the world by enriching the lives of our members through ongoing growth, development, and connectivity. And let me tell you how we do that. Education. SCTE offers hundreds of trainings, technology courses, boot camps, and many other learning opportunities that are free with your membership. Certifications that allow advancements through studies, exams for technology professionals looking to advance their careers in the industry. Standards. We offer ANSI, for those who don't know that acronym, American National Standard Institute accredited programs for everything from proactive network maintenance, next generation video technology, distributed architecture, Internet of Things, and many more. Career advancement. We support our members' career goals through mentoring, professional development, and certification. Networking. We organize a number of events, which we'll talk about more in just a bit, to help bolster relationships between MSOs, vendors, and other communities to support the industry. Technology and innovation. Through our partnerships with Cable Labs, we bring cutting-edge technologies to the forefront and into the hands of our members. Community outreach. We pride ourselves on getting the word out to the cable technology down to the ground level, into schools, robotics teams, and supporting scholarships for those wishing to pursue an education in technology-related fields. And if you're not a member benefiting from these great benefits or advantages, let me tell you how to become one. As you can see here on the screen, you can scan one of the QR codes. I know we featured Comcast. We haven't forgotten you, Charter. Charter members, make sure that you are logging in on your organization's website. Comcast, scan QR codes here, and all others, please scan QR codes. Be sure that you check in on an annual basis. You do not auto-renew. We want you to know to log in, check your member status. All access opportunities are something that is very new in 2023. We want everyone to know about free trainings that are now a new benefit for those that are in the all access programs. Opportunities that are offered, such as the one today. Also, if you are in the All Access program, you have the opportunity to join in Cable Tech Expo, which is something new that's an advantage being offered. Now, I'm going to move forward to certifications and tell you a bit more. Many of our members are working towards certifications and have advancement opportunities in their careers, and have an opportunity to advance from anywhere from installer to engineer, with opportunities such as inside plant, outside plant, and several more. Additionally, SCTE offers certification incentives. If you haven't heard about these, they're great. We include reimbursement for all exam fees in addition to finance incentives to encourage participation. Here is an example or a look at some of the incentives that are available to you if you choose to work towards these certifications. Hopefully that's not too fast. If you're looking quickly, make sure that you log in, look online, take a peek at all the things that are available to you. As we mentioned, networking is one of the things that we take pride in here in the Rocky Mountain chapter, and many other chapters are doing the same. What we have coming to you very soon is our SCTE Rocky Mountain chapter golf tournament and mixer. Tuesday, June 20th from 4:30 to 8 p.m. And I'm going to slide this to the side so I can see. And Wednesday, June 21st, tea time at 8 a.m. is the Ridge at Castle Pines North Golf Club Golf Tournament. You can find information about these details on the SCTE Rocky Mountain chapter website. We are excited to welcome teams to come in and participate in our mixer cable games, and all of the events where we want our community to be involved. If you're unable to participate because we're sold out with different things this year, make sure that you get engaged and be a part of activities in coming years. But again, we definitely want to see great level of participation in our mixer and cable games on June 20th. The golf tournament is probably sold out, so we hope to see you again soon in the future. All right. And as you've heard me speak to, the SCTE Cable Tech Expo that is going to be featured here in Denver, Colorado, October 16th through the 19th. More details to come. So continue to find ways to connect with our local chapter. We'll make sure that we continue to share opportunities to engage with your community. And finally, let's connect. We want to ensure that we stay connected through the many channels, platforms that you see here, Facebook, our website, all the opportunities that you see, email, be sure you're reaching out. All right, and now for the guest of the hour. I am excited to welcome, and I should say we are excited to welcome to you today, Keith Schaefer, technical trainer and engineer at Harmonic. Keith is a top-notch network security, video, DOCSIS, CMTS, PON, cloud native, and systems engineer and manager with more than 20 years of experience. That was a mouthful. He has several years of continuing education within the industry and over the past 25 years. With a unique combination of expertise in networking, network security, cable industry, voice and video surveillance industry, DOCSIS, CMTS, and PON infrastructures. Keith has developed and designed data center and lab infrastructures for IP video, networking, and video security systems, DOCSIS, CMTS, and PON networks. We are extremely excited to welcome with us today, Keith Schaefer.
All righty, I'm here. Thank you for the presentation and the introduction. Now, Kevin's going to be my right hand. So if there's hands that's been raised, questions that's to be asked in that during the presentation, please put it in there. Kevin will let me know. I'll ask during intervals too as well if there are any questions. So I like the interaction. I hate PowerPoints by death. So what we're going to talk about today is a little bit about Remote PHY. What is Remote PHY? Why is it good for us? What is the difference from the standard infrastructures and in the CMTS, the DOCSIS side of the world? And so we're going to proceed. We're going to go through that itself. So let's begin. So in a little bit of the agenda, we're going to cover what is distributed access architecture, how it relates to and how it's very important with Remote PHY and Remote PHY technology. And we're going to go over the Remote PHY technology as well. So what is distributed access architecture? According to Cable Labs, it's the CMTS, DOCSIS video functionality that resides normally in the head end or hub or the HFC plans, as a lot of people know and refer to it itself, that now we actually move it out into the field and we move it closer to the customer premise and we move it to the node level itself. By doing that itself, we also have the capabilities of using fiber instead of using RF over analog. Therefore, we get more efficiencies when it comes to speed, reliability, latency, and not only security, basically with a 10 gig SFP fiber connection from the fiber distribution to the Remote PHY device that's in the actual node itself. And we'll go through more of that and discuss more of that itself. So with distributed access architecture, one of the main things we're doing is we're now working with a virtual CMTS. It's software related. With it being software related, we're converting the CMTS, the DOCSIS infrastructure and that technology over IP. And then we're able with the Remote PHY infrastructure to bypass what the normal RF over analog was with all of that equipment. we're going to use a 10 gig fiber connection. That 10 gig fiber connection is going to be connected to the Remote PHY device. That Remote PHY device is actually in the Remote PHY node that you see that strand mounted on hanging from the poles, or actually into the pedestal mounts that you see into the ground level itself. So we're bypassing all of that RF over analog itself. One of the things that's really nice about it, when we remove that RF equipment, the combining equipment, is the transmit, the receiving optics, and that itself. What we're able to do is remove it from the HFC plants, from the head ends. The other thing we're also doing too is we're bypassing now, instead of using the 9RU or 13RU chassis, which are very cumbersome, they're very large, approximately 400 pounds in weight for some of those. We're able to remove those from the racks themselves. Therefore, we're able to save on heating, air conditioning, and capital and operating expenses as well. With that being said too, we're now making the software-based virtual CMTSs with the software configurations and the applications onto them in a more of a virtualized into a cloud-native environment. Gives us more flexibility, gives us the capability to put this all on 1RU servers, and therefore when we look at those feature sets itself, we're gaining a lot of space into the head ends. We're saving capital expenses because of HVAC, because of power, because we don't have to be concerned now that if we're needing to increase the actual HFC and the head end plant size, that we have to worry about tearing down walls and building new infrastructures and adding new hardware with it itself. So it's really, really nice. It's pretty cool when we start getting into it and start seeing more of the functionality and how it works. So in a standard plant, when we look at an HFC plant, we always know you walk into the door. When you walk in, you'll see the rows and rows of the racks. And with those racks itself, you'll see the different servers, the different appliances that are based within the RF technology, which is within the actual CMTS, the iCMTS chassis. And with that being said, when you look at the picture on the left-hand side of 192 service groups, as you can see, we have multiple racks of equipment. Because of the fact that we're using a virtual CMTS, we're using the 1RU servers. We in a cloud-native environment, 3 of them is what we're needing. With 3 of those, we can actually run up to 112 Remote PHY devices into the field, or when we look at the RPDs, we'll also call those the service groups. And so when we look at 192 service groups, and we can see it in one rack for those 42 or 49 RUs, it looks like that we have a lot less space that we really need to do for 192 service groups when it comes to that with the multiple service groups. So that's one of the big factors, as we were mentioning. We were talking about where we start pulling out the old equipment and we're putting in the new equipment when it comes to the virtual CMTS infrastructure, therefore saving a lot more space, removing equipment from the rack, more power in that itself. One of the big improvements when we get into the distributed access architecture, because of the fact that we're using fiber from the actual HFC, from the fiber distribution, the DAAS switches, the distributed access architecture switches, going to the SFP, the 10 gig interface on the Remote PHY device with the IP base, as we improve our MERs, our BERs, and also signal to noise ratio. When we're able to do that in that particular environment, it's much more controlled. Once we get the IP based into the Remote PHY device, then what it will actually do is we convert that into RF that will move to an RF amplifier, an RF tray itself that connects to the ports that will connect to the taps and the actual amplifiers into the field itself. So it's a different infrastructure. It's an improved technology. One of 2 more additional components that are really, really nice with it too, because of the fact that we're using the fibers, the fact that we can actually increase bandwidth as technology into DOCSIS 3.1, into DOCSIS 4.0. We're able with that to also increase the bandwidth, or increase the distance itself, and we're getting into ultra DOCSIS 2 that's going to be coming up later on, and we'll briefly touch base onto it itself. So with that, as you can see, it's a real big cost saving factor itself. So DAA implementation looks like, so distributed access architecture, our hubs, our head ends are updated with virtual CMTS chassis and the core routing engines. What the core routing engines are is they take the place of doing the layer 2 and layer 3 technology. 2 1RU switches such as the Arista or the Juniper brands. And with those being in place, with the 2 of them, we have our high availability and our dependability with those 2 as well. And the virtual CMTS, as I mentioned, they can run into a 3 server into the cloud native environment. That's software based and application based. The IP based now, so we're converting all of the CMTS, the DOCSIS technology across IP. We do an IP connection to the Remote PHY node into the field. It's into the RPN or the Remote PHY node that's actually into the field itself. We can run full 3.1 capabilities when it comes to the DOCSIS, improved performance, fiber reach, as I mentioned before as well. The one thing I want to mention with this is because of the fact that we're doing virtual CMTS and it's software based and we're converting it into IP, is therefore then we need the RF. So the Remote PHY node itself actually will convert the IP, the CMTS DOCSIS from the IP based into the RF. And therefore you have connections from the Remote PHY node that are RF based for your 1 downstream, your 2 upstream capabilities to the RF tray. And then it will have the RF ports and the outputs that will actually connect to the taps and the amplifiers that's out into the field. The extending the capacity with ease and comparison, we know when we're putting in iCMTS chassis, there's a lot of cost that's involved, a lot of wiring that's involved, a lot of additional equipment. And therefore, in a virtualized model, what we're doing is we're able to basically put in a 3RU for the virtual CMTS. If we need additional layer 2, layer 3 switch for that equipment too as well, then we're looking at 2 RUs for those as well. So in real world considerations, compute network resources and the locations, we can co-locate, so we can actually locate in the same hub with the Remote PHY device. In more larger MSO environments, we're not going to have the distributed access architecture switches located there. They're going to be further out into the field. And then from there, they're going to have their 10 gig SFP connections that are going to go to the RPD. You can consolidate in a reduced number of hubs. You can centralize it in such as a data center. So with some of the enterprise developments that have gone on with Remote PHY, that we actually see a lot of the virtual CMTS in a data center. And so they're being distributed and being connected to the Remote PHY nodes and the Remote PHY devices into field in a centralized environment. More of the edge or distributed architecture to where we'll see the virtual CMTS chassis that are going to be in the HFC plants or the head ends itself. So there's a variety different ways you can do it with a lot of flexibility with multiple Remote PHY devices that are available into the field. We have any questions at this time?
Nothing so far in the chat, Keith. Looks
okay.
like we don't have any requests, so I can bring up a question though.
Yes,
so
please do.
So what happens? You've taken all this power out of the hub sites. Is their outside plant going to require more power?
Is what going to require more power?
The outside plant. So
no. The good thing is, Kev, that's a perfect question. I mean, thanks for bringing that up. So the Remote PHY device that's going in there is going to use the same 40 to 95 volts AC, your quasi square wave that you're currently using for the nodes itself. So that's what's really nice about the Remote PHY with the hardware in that itself. It's basically been built, designed, and engineered, and with a concept and architected to be able to use what's currently out into the field without having to forklift and replace all the equipment itself. So
further to that, Keith.
Yeah.
So, and as we replace analog optics in the hub site, are you saying then that the Remote PHY unit or module that goes inside of a node, will that, I'm assuming that'll take more power than the current HFC analog optics?
Nope, it does not. Nope. That's one of the good things that coming in with Kevin, with the equipment that's being applied. So when we look at this and the thing, when you're talking about the power that's going into the node itself, so there's two ways to look at it. There's a current plan that can be added to where you use an adapter plate that works into the current analog nodes themselves. And then you put the Remote PHY device of it. It uses the DC voltage that's supplied by that particular node. So it will actually run the DC voltage for the system itself. When that system is fully loaded with the fiber SFP connections, that it's right around 32 watts. That's it. So it's not a power consuming, power consuming technology in comparison with what you would think, because of the fact that most of the electronics in that are made for the low power consumption in that itself. If you're going in and putting in a Remote PHY node, a brand new node that's Remote PHY based, the full chassis itself can actually run two Remote PHY devices. With the two Remote PHY devices, you have your AC to DC power unit, converts the AC into the DC. You can have a second power supply within that unit itself, or you can actually have a UPS device. So now we have a UPS device from the Remote PHY infrastructure that gives you a short term for brownouts. The RF tray off of the units themselves. So when we're looking into it, we're not looking at using more power levels, Kevin, when it comes to the Remote PHY. In a lot of cases, you're going to be using a lot less than what we've been using in the analog side. But a good question.
Thanks, Keith.
You're welcome. So Remote PHY technology goes back to the 7 layers of the OSI. Mostly when we looked into it, it was physical layer, data link layer, and then the network layer was based upon the cards. And off the line cards, we would actually have our interfaces that would be going into that are coax based, right? They're based upon fiber, are based upon the coax cable based side of the world. Now, since we're getting into more of with the Remote PHY using the fiber, that we get more into now a lot of the transport and the network side itself. And one of the reasons that we were talking as we talked about before, we were doing RF over analog. And with the RF over analog, then we're running that RF technology out to the field. We're talking about keeping power levels up, those things itself. So really with Remote PHY, we're still utilizing those OSI layers. And now what we're doing is we're making it more applicable to be into the session, the transport, and the network base itself. So in the hardware, if we're looking at iCMTS hardware, iCMTS, Cisco CBR8s, 64 service groups. And if you have 64 service groups, that means you're using all line cards. In most cases, a lot of the MSOs will be running 56 service groups because they want one line card to be for redundancy. It's a 13 RU chassis, hardware CMTS router, all based within that. Your timing and synchronization are all based off of the DTI, the SPA cards for the routing and that itself. So as we mentioned, it's approximately around 400 pounds when it's fully loaded now. When we get into the PHY portion of Remote PHY, we get into the connectivity, all of the data processing, aggregated, the routing, layer 3 forwarding, QoS, downstream bondings, downstream MAC, modulation, all of the relationship when it comes to the DOCSIS and the CMTS and now being converted to IP gives us that capability to the virtual CMTS are converted into IP. And then what we're doing is we're making 100 gig connections into the layer 2, layer 3 switches. So there will be a dual set of 100 gig interfaces on each one of the servers. One side going to the first switch and then the second 100 gigs going to the second side. That gives you the clustering and cluster mode for redundancy. And with the three, the cloud native and the cluster, you'll have the three servers. So therefore, with the software, the application side in the cloud native environment, what's really nice about cloud native is cloud native in a containerized environment with Kubernetes also has active and standby for your services such as DEPI, UEFI, MULPI. Any of the services related will actually have redundancy there. You'll have an active session and a standby session. Kubernetes kind of like the king. I call him the control freak. He's in charge of everything. So what Kubernetes actually does is Kubernetes will be monitoring what's going on with the system and the infrastructure in a cloud native environment. And when one of the active pods or container sessions has an issue, it will move it to the standby. Therefore, it doesn't cause for a customer issue. It doesn't cause for the customers to lose sessions. And then in return, when the standby session becomes the active session, then now what Kubernetes does is go back into what's current as the failed or the issue problem, such as the pod or the container, and we'll fix it and put it back in as a standby position itself. With the 3 1RU servers in one of the things I want to mention too as well, that in a cloud native environment, we're normally used to saying physically that they're called servers. When you start getting in the cloud native environment, they like to call them nodes. So when you're on the command line and that, you'll notice that a lot of them, the infrastructure, the results are called nodes. So with your 3 nodes or your 3 servers, you can do 112 service groups, or you can do 112 of the Remote PHY devices into the field itself. With that, now the capabilities of Remote PHY, we're actually able to move our bandwidth up to 1.2 gig or 1218 megahertz. And with the DOCSIS 3.1, and we'll cover that a little bit more into the field, as I mentioned to you, with the node, the chassis, you can put a single Remote PHY device into it, or you have the capability of doing a dual RPDs or Remote PHY devices into it. And we'll see that. We'll talk about that a little bit more as we go on. So what is Remote PHY? It's basically, it pushes the physical RF layer, as we mentioned, to the edge side. So what we're doing is we've converted that into IP, the DOCSIS and the CMTS, everything related to that. And then we're using the 10 gig fiber connection and going from the distributed access architecture into the Remote PHY device to the SFP. Then the Remote PHY device will convert that from IP into RF, connect to a RF tray or launch amplifier board, connect through the RF ports into your taps and to the amplifiers that you currently have that's going to the customer premises. So upstream, downstream channels, video, voice on demand, voice or video on demand, broadcast video, voice over IP, that's all still function. That all works the same as it has before in the standard iCMTS and the CCAP industry and what's been going on. So there's nothing that's been changed. You don't have to put, I call them additional trinkets, as one of the customers called it, which means that basically you don't have to buy a bunch of other little devices or appliances to make this system and infrastructure work. So in a standard virtual CMTS and a Remote PHY infrastructure, we would have, as you can see, our corporate network. Corporate network is where we're going to get our video from. That's where we're going to get our DHCP, TFTP for the cable modems and that itself. So from that corporate environment, we would actually be connected to with those core routing engines or those layer 2, layer 3 switches. We'd have our cloud native servers or the nodes themselves. The 3 of them would be connected via the 100 gig interfaces, as I mentioned to you. We'd have a telemetry and log proxy server. The telemetry and log proxy server, what it's actually doing is pulling all of the information, all of the data, the telemetry information, which is much more robust with a lot more information available than standard logs. And it actually will be saved upon that telemetry and log server itself. And with that itself, it's also a sending that back to a centralized area, and that centralized area will, there's multiple ways you can do it, such as a portal, dashboards, things of that, in order to be able to view your current system infrastructure, looking at details about the system, the remote PHY devices, the cable modems themselves, your downstream, your upstream channels, what's going on with your layer 2, layer 3 switch. So it gives you a lot more capabilities. Plus, the other thing, it gives you a lot more retention when it comes to the telemetry and the log information. You can go back as far as 6 months to be able to recover that data, where a lot of times with the log servers and that, you'd be hard pressed to go back 30 days to get information to as well. So if you're seeing problems or issues on it and you want to try and do a time scale for troubleshooting, it gives you more flexibility, more capability. The video engine, as you can see into the picture, which is a device that will actually convert the MPTS multicast over UDP sessions into an MP or SPTS as well, into those infrastructures. And with that itself, what we're able to do is to convert them into an MPTS over L2TP that's utilized in the remote PHY. Normally in the iCMTS side, we'd be using the DTI cards for timing and synchronization, and in the remote PHY, we're using PTP, our Grandmaster clocking servers, and with that itself, they're more robust. It's a better timing device. We use it for not only the CMTS and DOCSIS side of the world, but we also use it for the virtual CMTS software application with the remote PHY devices, and timing and synchronization with the remote PHY devices too into the field. On the distributed access, we'd be coming from the connectivity from the core routing engines. Therefore, as I mentioned to the corporate network, the remote PHY infrastructure and equipment are connected to that. Then from there, going to the remote PHY devices in the field for the 10 gig fiber interfaces, we'd be going from the DAAS, the distributed access architecture switch, 10 gig SFP connection. From there, we would go to the remote PHY device, the remote PHY device to the SFP there, and then from there, it's going to convert it. In the conversion, you can see into the window here, just to make it a little bit. We can see from the SFP interface, it's actually showing or listed here onto the remote PHY device. And then we'll actually have the RF for the 1 downstream and the 2 upstream capability, or 1 downstream and 1 upstream capability, depending upon the MSO and the customer base itself, via the mini coax cables. And that's the RF that's going to the RF tray. And then, of course, it handles the connections going to the taps and to the amplifiers that's actually out into the fields themselves. And then, of course, the housing looks basically as most of the other housings do themselves. So with that being said, the principal core DOCSIS high-speed data protocol that's used, communication, how are we talking back and forth, which protocols are being used. So into that, we actually have the generic control plane and what it is, our GCPP as well, that you can go hear it called as well. What we're doing with that is the protocol that we see, that the communication between the remote PHY device and the virtual CMTS. So when the remote PHY device, you add power to it, the first thing it's going to want to do is get its IP address. So a DHCP address communication gets its IP address. With that will be the DHCP scope options, and of course the IP address of the virtual CMTS core device. And then of course the RPD is going to communicate to it, and the virtual CMTS will push that configuration to the remote PHY device itself. As we talked about, narrowcast video, broadcast video, all run through the remote PHY device, and then of course to the customer premise, to the set-top box, or to the QAM tuner device that's being utilized itself. A lot of times, especially into broadcast video, we don't need to do, or we're not needing to do, any intercommunication back and forth between set-top boxes, but in narrowcast video we do, and so therefore the Remote PHY supports out of band for not only the video side and set-top boxes, but also out of band can be utilized into cable modems or other resource managing devices that's out into the field. So there's nothing left behind, nothing it can't do when it comes to what the current standards are and what's happening onto the infrastructure itself. So pretty much all of the alignment, all of the manufacturing, all of the engineering, architect design, nothing's been left behind. Everything is pretty much taken care of and also covered and are part of this. So what role does the digital optics play in Remote PHY? The SFP or the digital optics, as we discuss, are the connections coming from the distributed access to the Remote PHY device. The big difference between the two of them is the DAAS switches are usually in a building that's, shall we say, temperature controlled in that, but the SFP that's actually out into the field that's being connected to the Remote PHY device is needed to be of what we call a high temperature, or meant to be outdoors, because as we know, we get into severe weather conditions. We have Remote PHY devices around the world that are in like -20, -30 degree temperatures, and even into the 120, 130 degree temperatures and desert areas and things of that sort itself, or on the edge of the desert. But with that being said, the electronics for the SFPs and that are made to be able to handle the extreme extremities from the heat and from the temperatures outside as well. So this is what an SFP looks like. I think pretty much everybody who's on here has seen an SFP, installed them, used them, connected up multiple devices by using SFPs. This is what it looks like. So this is, it's pretty unique and pretty cool in the fact that you have a little small device like this that plays such a big role into it, to where you start removing and getting away from RF over analog, and now you're doing it IP, and where the SFP comes into and plays a big factor. One of the things, as we mentioned with the SFPs, by using the fiber and by using that infrastructure, is we're able to go further along in distance, and we're able to actually have more bandwidth, as we mentioned in the DOCSIS 3.1 with 1218 megahertz versus your standard 1 gig plant that goes up to 999 megahertz. The thing that's really nice too is the SFP capabilities. You can actually go up to 80 kilometers. Somebody's going 80 kilometers, Keith. How far is 80 kilometers? It's 49.7 miles. So you can actually have an SFP from a distributed access architecture switch, make a connection to an SFP in a Remote PHY node 49.7 miles away. That's a pretty long distance to be able to do so. So, any questions on that? A lot of time people say, is that fluff you're talking? Is it really true? Does all this work? Yes, it does.
No questions, Keith, in the chat. I have a question though.
Yep.
On your 80 kilometers of the SFP, does that take into account the loss of a DWDM mux if you're using that kind of a network?
I mean, it's a good point. So normally when you're talking about that, Kevin, from the distributed access switch and that itself, no, but that's where your system architect with your fiber folks into the field, your field engineers and that, those are the individuals that most of manufacturers rely upon to say, hey, we have this, we're into the field itself. So like you mentioned, so normally would you be using a 10K or 20K or 40K support when it comes to that for the SFP itself? Yeah, but that's a good question, because that the SFP will into play, like you mentioned. You're normally, I'm sorry, I hear a chirping sound that was going on. So with that being said, like you mentioned, those are things to play into if you're you know, when we start looking at the architect and design, what's currently there and what's currently part of your fiber infrastructure, right?
Yeah, thanks, Keith. There's just a note in the chat that said we're all muted at this time.
Yeah.
Currently, I think we just want to have people, if they have a question, please type it into the chat, and then I can read it out loud, and then Keith will provide the answers. So That's the way these seminars work. So thanks, Joe, for pointing that out.
Okay. The remote connections, when we start looking at the virtual CMTS or 10 gig transport, one of the things we look at is each remote PHY device being a particular service group. And then, as I mentioned to you before, one of the capabilities that you have with the remote PHY node, with that type of node, is you can actually run 2 RPDs into it, which means that actually you can have 2 service groups within that one chassis. So within that remote PHY node that's hanging or that's into the pedestal. The other thing, if you're only using one remote PHY device that's into it, how easy is it to go in and do a node split by putting another RPD into it? So it's very simple. It's very easy to do so. So you put another RPD into the unit, you do your node split by just applying the fiber connection to it. And then from there, the configuration that you've done at the virtual CMTS side, and that's it. One of the other things that we mentioned too, we've talked about before, is full spectrums up to 1.2 gig or 1218 megahertz. You've got your standard capabilities of 158 singular carrier QAM channels for NXB with OFDM channels. So now your OFDM for the downstream side, you can do 6 channels, and you can do that up to 192 megahertz per channel. And then you have complete flexibility for QAM and OFDM for the downstream side as well. I'm sorry guys, there's some thumping going on from upstairs because I'm in the hotel room here in Dallas. On the upstream side, there's 2 gig for the upstream ports. The good thing is we can support that high split up to 204 megahertz for the upstream side, the 12 singular carrier QAM channels. And then of course we have our 2 OFDMA channels that are available up to 96 megahertz for OFDMA channels. And then, as I mentioned before, you can do a 1x1 for 1 downstream, 1 upstream, or 1x2 configuration options too for the remote PHY devices themselves. So you can do your 1 downstream and 2 upstream capabilities. Fiber deep spectrum. Once we get into the frequencies, as mentioned, we can do our sub, our mid, and our high split plans. And so therefore on our the capabilities and flexibilities onto it in the remote PHY devices themselves on the RF trays, it's just as easy as they have replaceable diplex filters on the RF tray for sub, for mid, and for high split plans. It's just as easy to take out those 4 diplex filters to upgrade your the plant size that you're wanting to do too as well. So that makes it really nice. A little chart here that you see on the right-hand side where it says head in, we can see the virtual CMTS going to the switch, the 10 gig Ethernet connection that goes to the remote PHY node. And then, as I mentioned to you, from that particular point, the RF tray, the launch amplifier boards have the port connections going for your taps and for your amplifiers set out into the field. So this is just a little nice little picture and showing you still the capability with it. The left-hand side, that's some of the node design operational levels. So those are the difference between your digital and your analog. You'll see your frequency, and then you'll see the approximation for the dBMV. It's not an exact science, but these are pretty much within those alignments that you'll see when it comes to the frequency and when it comes to the power levels that are actually being utilized. So it's just a little chart just to gaze at, not something that's going to be exact to a lot of the customers' configurations and that. This is a nice little picture of what a node looks like into the field, hanging with the strand mounts onto the poles. Everybody's seen this, right? Yep. Everybody's seen this too as well. So onto the side of the road, you always wonder what's in those boxes. What's next to that telephone pole? What's in those green boxes? So in those green boxes, those pedestals will be your nodes, and within the nodes are remote PHY devices themselves. And you can see that they're doing an installation into the pedestal with a new node itself. One of the gentlemen today said that it actually looks like a bunch of Department of Transportation workers, right? You got 3 guys and 1 guy doing the work and the other 2 guys And then it was kind of funny because another gentleman said, well, you know, when you're digging a 5-foot hole, you need to have a team because you'll get tired quickly for digging that 5 to 8 foot hole, and you need another team member to do it itself. So I thought it was just kind of comical and kind of funny. And then another real live where we'll see that testing's being done, checking the levels, and that as well too. So these are where we're seeing what the bandwidth capabilities and that are with the by using the meters. As we were looking earlier, talking about the Remote PHY device itself, within the Remote PHY device, we can see that there's 3 SFP connections to it. By default, the first connection goes to the first port onto the Remote PHY device. The second port can actually be used as a, if you want to cascade the 2 devices. So if you have a second RPD into it and you want to cascade the 2 of them, you can go from port number 2 to port number 1 on the second device. The thing that gives you that capability, but remember, if you're doing that, the problem with that is you're still utilizing the 110 gig connection. So there are purposes for it. We have customers that ask for it and customers that want to be able to do so. The other thing that you have is flexibility with the port is with the cloud native application. Part of the application of the virtual CMTS. Also, too, one of the other a couple applications that can be utilized are the virtual OLT or the virtual BNG. And with that being said, those actually are used for PON. So you can use a FIN or OLT device that will plug into the Pebble. So with that being said, that with that same 3 servers, with that same application, you can be doing DOCSIS and CMTS, and you can also do PON to it as well. So that gives you a lot of capability and flexibility with that into the field itself. The other thing that's nice when you start talking about virtual CMTS software-based, communicating to the Remote PHY devices into the field. IP-based is any changes into the system, and that can be remotely done. And what's is really nice because you don't have to send a field engineer to go out and start tweaking, making power level adjustments or attenuations, so that or tilt configurations too as well. So there was a question that popped up, and that question was, what is the third port for? That third port is actually used for that OLT or for that FIN device. That's what the third port is actually used for. And the other thing is there's for power level AGC compensation and that too, that's available. And now with technology how it's increased in that over the years, you actually have a capability of what we call a V bias, and that V bias actually allows for you to start saving some of the power too, coming off of the RF trays and that themselves out into the field. So there's adjustments and tweaks for that too as well with the software. In a Remote PHY node, when it's actually open, Remote PHY node will have into your top section, you'll see the RF tray. With the RF tray itself, you'll see diplex filters. The diplex filters, as I mentioned, are replaceable. You have your coax, your mini coax cable. That's where the RF is coming from the Pebble. So when it did the IP conversion to the RF, you have your downstream and upstream connections for that itself. And then you have your ports that are for your connection going out to the taps and also to the amplifiers. You have your AC to DC power converter. So that's converting AC power into DC for your RF tray as well as for your Pebble devices. As mentioned to you, these are your Remote PHY devices, and then you can see the connections here that's going up to the tray. And then the other, as I mentioned, a UPS device into it. That's meant for brownouts. That's not meant for long-term capabilities. So especially into the areas where brownouts are done, when you lose the power to the Remote PHY device, the Remote PHY device will do a reboot and to have to come back up online. but in a short term in the brownout, the UPS will support that. So therefore, it keeps the customer online and doesn't affect or cause for the customer to go offline. Approximation in currently for the Remote PHY device from a reboot status will be approximately 5 to 7 minutes. And then the other thing is now with the capabilities, especially IP based in that, we get into handheld devices. Those handheld devices, we can actually put applications onto it. We can make adjustments to the power level for downstream, upstream. We can use it for part of the implementation into the fields and that itself. So that's what's really nice. One thing that's something to be aware of is Remote PHY devices. Since we're talking about IP based on that, the MAC addresses of the Remote PHYs are unique to each other. That the MAC address is used for the configurations for each one of the Remote PHY devices, so it's very prevalent and very, what I want to say, it's a very big part of the configuration of the system. So if the MAC address is incorrect, the RPD will not work properly, or you could assign a MAC address to the wrong RPD configuration. So those are things that where by scanning the QR code and that itself, when you're at the site, you can verify and validate too as well, which is really nice. R-PHY architecture and flexibility, as we mentioned. So we're used to the term of CCAP. CCAP allowed for us to use the ICTM chassis, iCMTS chassis allowed for us to be able to do our CMTS, our DOCSIS. We could do video and we could do our voice over IP and in out of band if necessary in that itself. What's nice about R-PHY, it's more software based versus the iCMTS was a hardware based setup onto it. You have different Remote PHY devices. So on the Remote PHY devices, we have some that are called the shelves. Shelves can actually be used indoors, those indoor devices. You have different nodes. You have different nodes out there that are single Remote PHY nodes. So you can put one Remote PHY device into it, as we saw before, where you can also have a Remote PHY node that does 2 RPDs or 2 Remote PHY devices into it as well. Better capability and flexibility when it comes to the devices of putting them in data centers, the head ends, or the HFC plants, and then also the remote hubs too as well. And of course, outdoors when we're talking about the Remote PHY nodes. Okay, so that's the end of the Remote PHY session. What questions do we have?
Okay, Daniel, are you there?
Hear me?
Yep.
Awesome. Well, thank you so much. I really appreciate this presentation today. It's fantastic. I want to ask a question. At the Cable Next Gen conference in Denver earlier back in March, SCTE made there was an interesting detail regarding vCMTS, which was SCTE stating that there is a potential power savings in the move to vCMTS of something like 2 to 2.5 times, the CMTS configuration. That they're sort of predicting this kind of power savings as possible. And I wanted to ask if if you're aware of that sort of statistic from SCTE, and if that has to do more with the move to Remote PHY and moving those components out of hubs and head ends, if that's where the power savings come from, or if there is I just wanted to see if you could comment on where that potential power savings actually comes from with vCMTS. Is it from R-PHY or is it from some other aspect?
Well, that's a good question. And the one thing to remember in the Remote PHY, that's also part of the virtual CMTS in the plant area, right? So that's part of it. But the big thing, like you mentioned, within the plant itself, that's where the hardware of the RF over analog and the iCMTS chassis are being removed and they go away. With that being said, because you're using less equipment now, because you're using one RU servers and also the switches themselves and going in, therefore it's less air conditioning, less power that's needed and necessary too, because these things, what I want to say, they handle the power distribution that much better, right? In a server base compared into an appliance based itself. And the larger the device, the more power it actually needs in order to work and operate. So just, from that perspective. And then I can tell you too, from what's currently out into the field, what's been going on with the Remote PHY within the industry itself, that the customers already seen big impacts. So you're hearing big kudos that are coming in from the financial departments because of it itself. It is that much of a difference when you're working with Remote PHY in the HFC side of the world too, about virtual CMTS servers, and then also in the switches, because the fact too is that there are a lot more, they can handle more capabilities and handle more devices. Into the field itself, as mentioning, in the Remote PHY nodes and that, with the newer technology in that itself, one of the things that is found is that it's using less amount of power needed for the infrastructure that's within that actual Remote PHY node itself. And so therefore, as I mentioned to you before, there's also capabilities within the software virtual CMTS to actually decrease power consumption of areas within the RF tray. If ports aren't being used, that those particular ports can be turned off. Those capabilities, those flexibilities that you actually have within the system itself. So there is also seeing power reduction into the field as well. So with the accumulation of both within time itself, you'll see that your financial people, are really very happy about it too. Plus, one of the other things for us itself is usually when we see that units aren't pulling as much power in that itself, that we get a little bit more longevity from the devices, especially into the field side itself. All right, let's take 5 minutes real quick, and then we're going to jump on to PON. I know some of the folks are on during the morning session. The morning session had a lot of, at the facility I was at, had a lot of field engineers. So there was, some of the interactions, some of the questions, and that comes back through to discussing what they're seeing into the field, or what they're really concerned about, or things that they're, how is it relative to Remote PHY? What is the difference? Things of that sort. So, those are always good stuff to bring to the interaction and to the conversation pieces.
It looks like maybe Martin would like to get unmuted to ask a question.
I was just going to say, yeah, in the spirit of your comments there, Keith, let's see if we can get Martin on. You're there,
Okay.
Martin?
Yeah, I'm here. Can you hear me?
Yep.
Okay, I was just wondering, as we launch the DAA now, or launch and say with up to 210 gig, what's the future bandwidth for DAA in the RF plant? I mean, is there a future of what you think we're going to get to, and how do we keep expanding the DAA after the 210 gigs are utilized, or is there a plan to go further?
Oh, you mean as far as like, then do we start putting 25 gig connections and that onto them?
Right, or 40 gig, and then will the DAA support what DOCSIS platforms, what modulation is the RF going to go to too as well to support? How far can it go? I guess the DAA and the RF combination, or the coax combination.
Yeah, and then I'm not sure, Martin. I think that's, like you mentioned, those are things that's a little bit of the future that I can tell you right now. I mean, I keep up to date, from our team members when it comes to, like you mentioned, from R&D, also from our networking team, and as far as the marketing side, and then advanced engineers and that too. And pretty much right now, I haven't heard, most of it's all focused on the 10 gig, but I have not heard, or there's probably other talks going on that I'm not privy about, or that I've heard about itself. So it's been more the flexibility of the product, introducing additional product. And then of course, PON is becoming such the big factor itself too. So,
right. But in the areas where we don't have PON, how far can we go with the coax plant to compete with our overbuilders and things like that, as well as getting at, I guess.
That's true. I mean, it's,
I could jump in, Martin. The
Yeah, go
DOCSIS
ahead, Kevin.
4.0 cable lab spec goes out to 1.8 gigahertz
Yeah.
or 100 megahertz. So to do that, you do require a DAA architecture, whether it's Remote PHY or Remote MAC-PHY. So the next generations of RPDs or RMDs will support out to 1.8 gigahertz. So that's the current cable lab specification out.
Yeah, the one thing, I mean, that's good, Kevin, that we can go into the, like you mentioned, the 1794 megahertz, right? But that gets us to that. But it's, I mean, like Martin was saying, then is that going to require that we get more out of like the 10 gig side of the world, that we get into more bandwidth, right? From that perspective. It's a gotcha. It comes across with everything. So, yep. All righty.
Thanks.
You're welcome, sir. And we're going to talk a little bit about PON. We're going to talk about passive optical networks, or introduction to PON. So we've been talking a little bit about Remote PHY. There's going to be some relationship with PON, relationships between Remote PHY and PON, relationships to what's happened with DOCSIS and CMTS. So we'll talk about a few things. So one of the things that's part of this is from the PON is we are one of our management team members that's part of Jorge, that's part of this, puts together great PowerPoint presentations and that for the stuff. And I like to go and steal his material and use for whenever I do my stuff. And I have Jorge's approval to do so. So in the case of this, there's this summary and introduction that's kind of pulled from 3 different areas of some of the documentations. And one of it's relative to what we see in smart cities, but it's a little bit more than just smart cities. So in PON, in introductions, what we're starting to see is with fiber's already there. Fiber is being utilized. We need it basically for such as a city infrastructure, for resources to be able, for highways, for detection devices, for cameras, things of that sort. Buildings, water department, power, waste. There's different detection devices that are IP based now. Schools, central, what do we want to say? Central for access control, central for security purposes, and that itself. Libraries, crime detection, working with the police departments, with the sheriff's department, and that itself. Also, too, as I mentioned, the different sensors and cameras that are out into the field, IT resources, data centers. A lot of times that cities in large areas are using data centers for their capacity, for their internet access, distributing their network connections or network connectivity and that itself. And then also too, that connectivity, they need a fast and reliable network. And of course, that's where it's fiber. You won't see coax and that out into those areas. It's all fiber based. Also too, within 5G or within the cellular community itself to where it's being used. So one of the things we know is whether it's large campuses, large data centers, large distribution areas such as warehousing, things of that are using PON because some of these actually are like little small cities or smart cities where there's a lot of different buildings and infrastructures. And this is where PON comes into play and is being utilized a lot too. So fiber network, a 2 gig, symmetric network. And we know now that we're even getting into 25 and 50 gig when it comes to PON technology. Provides capacity and efficiency. One of the things is we can do a point to multipoint. Within that PON, we can do an OLT, a thin device, and actually go to a 1 to 128 means we can put 128 devices and connections up with that one single OLT. So we can put hundreds of devices on a single fiber connection. Basically, we're doing a passive network, so we're improving cost savings too. Then we're able to reduce operational complexity because of the fact that we're using the fiber that's currently there without having to to remove and start adding new equipment in, and enable basically the future revolution, as I mentioned to you, with the 25 gig, the 50 gig, and even at the point where 100 gig symmetric speeds are coming into testing and that itself. So PON 01 on passive optical network, basically no active components and better reliability. Basically, it's fiber all the way and more bandwidth capacity. So in a lot of the MSOs now, a lot of the MSOs are doing fiber to the business and fiber to the homes. And so therefore, we're having ONUs and ONT devices that are into the homes themselves and also into the businesses. And that gives them more bandwidth capabilities. And point to multipoint, what that gives you, it minimizes the fiber build out versus a point-to-point connectivity. Our components we use are the optical line terminals, our OLT devices. These, a lot of them are called fins. You'll hear them called fins. They look very much like an SFP, but it's a little bit bigger with some fins onto it for heat dissipation. Your optical distribution network. So in the optical world, when it comes into PON and into the fiber, we talk about attenuators and we talk about splitters. And then we'll get into the ONUs or the ONTs. Those are basically, they're very similar to a cable modem, but they're fiber-based. And so within that itself, those are your ONUs, ONT devices that are actually at customer and business premises that the fiber connection goes into that particular point. There are customers and areas where we have point-to-points for PON. You know, a lot of times it's relative to security purposes, to where the different type of industry, different type of companies, or the government, airports, things that want a point-to-point to be more secure than that versus a point-to-multipoint. So therefore they'll utilize it, but it's definitely more expensive, but you can still do that capability as well. Point to multipoint, so we can actually use the three concepts of the tree, the bus, and the ring. And so it gives us basically, we can do a one OLT. From that OLT device, we can actually run through the splits and then run into multiple different ONUs and ONT devices as well. So for the upstream and downstream information. And we can also look at the ring, and the ring gives us a little bit more of the redundancy in that with that system set up too as well. So there's multiple ways of connection, connectivity, and using the fiber when it comes to the PON side of the world. Similarities between DOCSIS and PON are basically both are point to multipoint networks, a centralized controller. So in the CMTS side of the world, for DOCSIS, and then of course on OLT, those are the area that distributes the traffic across the multiple users, either to cable modems and the CMTS DOCSIS side, or to the ONUs or ONT devices that are out into the field. Transmission mechanisms. So PON is very similar to earlier versions of DOCSIS, and then of course when we talk about TDM and the downstream, and then TDMA and the upstream side of the world itself. Main differences between DOCSIS and PON. So remember, when we're talking DOCSIS, more of this is related to the RF coax side of the world, not when it talks about, when we're talking DOCSIS here, is not about PHY so much, remote PHY, as it is to the standard DOCSIS over coax in the RF analog side of the world. And then in PON, we're looking at light and fiber. In DOCSIS, we have modulated QAMs and OFDM channels, right? On PON, we have baseband. The DOCSIS side, we have variable power output. That's where we talk about whether we can adjust and set power RF levels for the dB and V. On the PON side, the power outputs are fixed. Configurable frequencies for the DOCSIS side. So you have a handful of frequencies to be able to use for your QAM, your singular QAM channels, and then also for frequencies used for OFDM and OFDMA. And then on the PON side, we use a wavelength for the different types of PON technology. We have channel bonding in the DOCSIS side of the world. And of course, with DOCSIS 3.0, that's the biggest thing. That was such a big plus, being able to have channel bonding to increase the bandwidth and capabilities when it came to DOCSIS. And in PON, currently, as we can say, there's no bonding yet, but I know that being told that there will be bonding in some of the newer flavor of PON coming out. DOCSIS, you can go up to 160 kilometers. It's not something I would do. Just because Cable Lab tells you can do it doesn't mean it's something that you want to do. But there is that capability of doing it. On PON, you can go approximately around 20 kilometers. The good thing is with PON, we normally think of in some of the PON infrastructures and builds and that, we're talking about big boxes, big appliances, that you have OLT that fit into these switch interfaces. And then within that itself, then you're going out to the ON through the splitters and going to the ONU and ONT. And we also have now the capability with PON that we can run from the actual distributed access architecture, run the SFP connections to a Remote PHY node. And in the Remote PHY node, instead of having RPDs, we can actually put PON switches that actually will go inside those devices, getting those PON switches, those capabilities closer to the customer and to their premises and that itself. So that's also flexibility that's available now too as well with PON. And then contention-based bandwidth requests from the cable modem. So you're constantly having that go on. But OLT basically pulls the ONUs for bandwidth requests, and then it's available at those particular times. So PON is much simpler protocol than DOCSIS. It's a given. Any questions on that? All right, we'll continue. So traffic flow on the virtual CMTS, we have our internet, our core routing engine, working through the virtual CMTS, and then we'll have our communications through our core routing engine, and then to our switches, our DAAS switches, and then connections to the Remote PHY devices, and then of course we go to the end user, and that's where the cable modems are actually connected in that itself. And then, of course, we have our upstream and downstream channels with it itself. So on the DOCSIS side interface, that's where those connections in that. So DEPI and UFC and UEPI encapsulation over L2TP follow within those traffic frames itself. So within virtual CMTS, we have a lot of classifiers, a lot of filters, a lot of COS, a lot of QoS that's all hidden and kind of part of the configuration that's into the background. Traffic flow on PON is similar, but with some variances and with some differences. So on the internet and the core routing engine side, of course, as we mentioned, we go to the virtual BNG and to the virtual OLT part of the application. As I mentioned, that's part of that the same cloud native infrastructure. On the CLAN configurations, and then from those CLAN and VXLAN configurations, those are actually going through your switching and then to the FIN OLT, and then from there we're going to the users, to the ONUs or the ONT devices that are out into the field itself. So cable modems versus ONU provisioning. So on DOCSIS cable modems, they're layer 3 autonomous devices. Basically, in the DOCSIS side of the world, it talks via the MAC and the MAC frame and the MAC domains to the CMTS. Once it does that to establish, to get power levels and that, then it'll get its IP address. A lot of DOCSIS cable modems now are getting 2 to 3 IP addresses for those cable modem devices. You download a provisioning file via TFTP, so that configuration file is on a TFTP server that gets downloaded to the cable modem. And then the cable modem will negotiate with the CMTS for the service, and therefore you're having MAC management messages. And the other thing is those MAC management messages are continuously ongoing back and forth between the cable modem and the CMTS device. PON ONUs are more layer 2 devices that are slaves to the OLT. There's no IP address. OLT programs for ONU provisioning are done, and then OLT learns the provisioning from the command line, the SNMP or net configuration. That's learning of that and getting that information on the OLT side. So from the application side, for what we saw, the virtual BNG, the broadband network gateway, from those devices, we're able to see the provisioning itself from there for anything relative to the OLT for the FIN devices. On what is so good about its reliability, why is it such a big plus? One of the things that we've talked about, it's an all optical network. There's no coax that's involved into it, so we know it's less sensitive to noise than HFC. 4 major factors that influence part of the performance is launch power. One of the things that we know, we have output power that's coming out of the laser. One of the things to be concerned is some of that power can be a little bit hot. Excuse me. And one of the things that is very important when in PON and coming off the fins, with those power levels being so strong, we have to make sure we do attenuation at the splitter levels and that itself before we get into the ONUs and ONTs. So just, it's just some food for thought. Receiver sensitivity. So we have minimal light levels that a receiver can detect, which is nice. So loss, anything that contributes to optical power degradation. So we know this has been ongoing. It's not anything new, but of course, distance, how far the fiber runs are, splits, if there's splits actually into the fiber, connectors, and also splices as well. So those are anything that attributes to the fiber. So companies have been working with fiber for years. They know all of the ins and outs, and the best way is to take care of any loss or loss prevention, as we should say too. And then transmitter dispersion penalty. So that's basically the light pulse becomes distorted as it travels through the fiber. And there's nothing new with this, but the one thing is this: PON reliability is definitely better than what we're talking about when it comes to the HFC side with RF. PON standards, all kinds of them. For years now, we've been running through a lot of the PON standards and that. Where the conception of it came from, what started with it itself. So we can see back in 1996 where APON and BPON were utilized. GPON came in, XGPON and NG-PON2, and then XGS PON for the ITU side of the world, and then on IEEE, the EPON and 10 gig EPON. And then, of course, we've been talking and mentioning before, too, as far as 25 and 50 gig EPON as well. And then, of course, the old RF over G, right? So RFOG has been out for a while. It's kind of a dying breed. It's still out there. It's still being utilized, but we're starting to see it being replaced because of the fact it is a dying breed. It's hard to get parts for. It's hard to get replacements and that for it itself. So PON, when we talk about wavelengths, we talk about frequencies, and we also talk about the longer wavelengths. So we'll look at some of the PON technology in that itself. So when we talk about O-band, E-band, S-band, C-band, and L-band, we see that we have R-PHY for downstream and R-PHY for the upstream side. So 1550, 1560 for the downstream, and then the 1600 to 1620 for the upstream side. 1 gig EPON, GPON for upstream, and then GPON and EPON for the downstream as well. So we see the different frequencies that are utilized for those. GPON for upstream, that's reduced. And then we also see GPON for the narrowband as well. And then we see XGS and 10 gig EPON. We're going to see that those are most used. So we see the upstream and downstream that's being utilized for those, for the 1270 nanometers, as well as the 1577 nanometers for those particular, for that frequency as well. And then NGPON 2 for upstream and downstream. And then we start seeing 25 gig EPON for upstream, and also 0 and then upstream 1. ITU, when we talk about ITU PON, where basically they've been developing standards since the 90s. It was mostly focused on the telco market. One of the big areas where it came into in the telco market, there was a lot of twisted pair, and then the fact what they needed to do is fibers being run, and so they wanted to be able to utilize the fiber, and so therefore there's a lot of work that was done with the telecommunication side to be able to use the fiber. So that's where the GPON and the 10 gig and symmetric for the XGS for PON are the most widely deployed PON standards itself currently. GPON basically was created to transport different types of traffic. So we can think of, we have a big pipe right now, and within that pipe, we want to run different channels of different technologies, such as voice TDM. We want to maybe possibly do Ethernet. We want to do MPLS. So the good thing is with GPON, it allows for us to run those different frames, or what we want to call the X or GEM frames, and those are actually allows for us to send that down our PON fiber link, and then of course the ONUs and ONTs actually get the GEM frame and then distribute it as is needed and is being asked for itself. So that's where with PON frames, it's really nice. It gives us the flexibility to be able to do different services. I mean, if we want to do IPTV, if we want to talk about Ethernet, where we're talking about internet TV or IPTV using the internet too as well, that some MSOs are doing as well. Flexibility of being able to use the different VLANs for optimizing the traffic and traffic flow as well too. So it's really nice little setup with a lot of flexibility when it comes to PON. So GPON's been deployed, as we talked about, mostly by telcos. XGS started to gain traction in the last couple of years. And the NGPON is basically being utilized by Verizon here in the United States. And then one of the things, as we mentioned about too, is ITU PON is layer 2 oriented. So most end users are unable to classify based on layer 3 parameters. So as we mentioned, those are layer 2. And then OLTs are simple switches. There's no routing, as we talked about before. So one of the things to be aware of is the fact that there has been some companies that has made PON equipment, and their PON equipment is utilized. The ONUs and the OLTs are specific that they have to use. You have to use their specific equipment for using PON. There's not interoperability, being able to use different manufacturer OLTs or different ONTs. So that's something that has happened and become more available. Of course, they don't cost as much, but then also you have to be very, very careful because it's specific to that manufacturer. IEEE PON, Institute of Electrical and Electronic Engineers. We've been doing IEEE for different standards and protocols for years in our industry. And so therefore we know that's the body that created Ethernet and Wi-Fi, and then a lot of the other technologies that were part of it. So developed the 1 gig Ethernet PON, the EPON, and then also the 10 gig Ethernet PON. 25 and 50, those are standards that came out in July of 2020. They're being 25 gigs being used, as well as 50 gig that I know through within the industry itself throughout the world. So gives you That is correct, Joe. And okay, so you got me. All right, so back to the 25 and 50 gig. So as I mentioned to you though, so 25 gig is starting to be used more, and 50 gig is available, and I've heard of some customers using the 50 gig when it comes into those particular standards as well. So ONUs or ONTs support layer 3 filtering classification similar to cable modems. So we're starting to see additional too, where the ONUs and the ONTs have RF connections. So a RF coax output connection onto them. We're starting to see the ONUs, ONTs also to have a Wi-Fi capabilities and like a 4-port 1 gig interface connection off of them too, besides the 10 gig WIN port that's onto them. So there's a lot of flexibility, a lot of things that are going on with the devices that are being manufactured when it comes to PON for the ONUs and the OLT sides. So EPON is based on Ethernet. So when we're talking about that, we're talking about anything that's on an Ethernet side. What's really nice about that, Ethernet's easier to handle, right? We've been doing Ethernet when it comes to network infrastructure for a long period of time. So it's pretty well standardized when it comes to EPON, OLT, and ONUs, and provisioning ONUs too. So basically, they'll use a file for that too, very similar like a cable modem configuration file too as well. XGS PON, what's the difference between that and the 10 gig EPON? So XGS, we get the flexibility for being able to do different TDMs, Ethernet, SDH as well. So we can do different types of traffic. On the 10 gig, we're going to do Ethernet traffic only. The XGS PON is L2 centric and limited traffic and classification and filtering on L3. So as we mentioned, it's more L2, layer 2 side of the world. Layer 3 traffic classification, similar to cable modems when it comes to the 10 gig on the EPON side. And as I mentioned to you, we start seeing devices and that are having those capabilities on the ONU and ONT sides. Slightly more complex ONU management for the XGS, and it's a little simpler on the Ethernet side when it comes to the 10 gig EPON for management and too, because it's used in the Ethernet protocol messaging. And then no MAC addresses on ONUs when it comes to XGS. It uses serial numbers instead. And then on 10 gig EPON, it plays nicer with the DOCSIS provisioning and that itself. So similarity, same data rates, 10 gig symmetric, same optics, so which is nice. Same split ratio, so you can do up to 128 ONUs per OLT device, right? And then ONUs are based upon the latest Broadcom Cortina or T-bit chipset support too as well. So we see basically any of the ONUs, ON2 devices that you're going to see that mixture with those chipsets that are part of those systems and infrastructure. That's part of the IEEE and part of the standardization with cable labs and that itself. So it allows for you to use different ONUs and ONTs and OLT devices together from different manufacturers, which is nice. So we talked about the case for PON for smart cities, universities, airports, any area that's huge when it comes to size. You know, a lot of the military as well too. When we get into it, a lot of the government based office areas and that we see, especially in the DC area and that. So there's a lot of mobility, crime detection prevention, environmental connectivity, crime prevention, as we talked about itself. So there's a lot of flexibilities when it comes to the case for PON and for using them in smart cities, or as I say, into that large environment. In the case now with MSOs where they're using FTTH to both the businesses and also to the residential customers. So that means some of the largest PON distribution and infrastructure is going to be from the MSO side of the world. So PON is the point to multipoint network that's going to be most used as we see And then, of course, our OLTs, our splitter, and then we talked about our ONUs and our ONT devices. So what's the future? It's basically adding more bandwidth, right? We have 10 gig right now. Now we're going to be putting 25 gig, 50 gig capabilities, 100 gig capabilities. So we know that in Cable Labs, there's already some stuff is being done already for the 100 gig side of the world. So what are we doing? We're creating the need for additional bandwidth from different sources for different services, not only for residential and people at home, but also for the businesses. So we're going to see PON expand by increasing the capabilities for more bandwidth. Passive optical networks are ideal to provide connectivity infrastructures to smart cities and large infrastructures as well too, such as MSOs, as I mentioned. PON networks have a clear roadmap beyond 10 gig, which we already know. It's already started and being utilized as well. They provide 10 gig symmetric speeds, up to 256 devices from a single fiber. In most cases, as I'm going to tell you, on the OLT side, we're going to see a 1 to 128 relationship. And then SFP plus ONUs allow devices to be easily connected to PON networks as well too. So, any questions on the PON side? It's a quiet group.
Yeah, nothing in chat at the moment.
No.
Yeah, Joe's giving you some shout outs there, saying thank you.
You're welcome, Joseph.
Oh, and we got another one here. So from Vincent. Vincent's asking, can you talk about ONU on a stick?
I really can, because I'm not familiar with ONU on a stick. Trying to think ONU on a stick would be you plug it into a USB interface. I don't know, because I'm only familiar with, in all true honesty, and maybe because I focus in a particular area more so than all areas. It's probably due to I'm seeing ONU devices and ONT devices that are similar, like a cable modem, that go inside a home, or they go onto the outside of like their little their infrastructure where they're supposed to go into. But I couldn't say anything relative to an ONU on a stick.
It says like online. It's a GPON stick. It's SFP optical module with a built-in 1 gig ONU. Which,
oh, okay. So Vincent, where is that being utilized? What areas?
I just heard some references to that at Charter. So even though I don't have any, I mean, I've tested on normal ONUs, but I just heard some references to it. So I just remembered that. I was wondering if there's if you had any input or insight into that.
No, I wouldn't, Vincent. But Joe,
okay. I could do some research into that.
Yeah. But you know what? You made me curious. So I'm going to go out and look it up. So hopefully that for some of you, you probably already have worked into these areas or are familiar with. And for those of you that haven't, hopefully that you gain some knowledge from this, some good stuff. So if we don't have any more questions.
Yeah, just a couple more shout outs there and there. And
Thank you all. Thank you all for participating and being involved into this. I know everybody appreciates this.
Thank you, Keith.
Thank you, Amber. Well, with that being said, and nobody else has any more questions on that, I think we can call it a day. So everyone enjoy the rest of your evening in that, and thank you so much for joining.
have a great holiday weekend, everybody.
Yes, especially.